So far we are still doing the basic state being at rest. I haven't been giving details on the various assumptions in the simplifications we made, because throughout this chapter we look at horizontal flow and vertical flow and the vertical structure, but these are still idealized solutions. So the physics is important of how the wave mean flow interactions happen. So when we actually have to understand the physics, there is the full nonlinearity involved. So it's mostly about interpreting the tropical dynamics in terms of these basic physics that we are learning. So far we have looked at essentially wave kinematics without adding any of the basic state, which we will do soon. And we are now just going to add some vertical stratification to start adding more complexities to the longitudinal vertical interactions and waves we are looking at so far. So for the free system, frequency omega is the eigenvalue for sets of longitudinal wave number and equivalent depth, or Hn in the longitudinal vertical system, right? Remember, when we have been doing just the longitudinal system without worrying about vertical structure, where we kept talking about equivalent depth. Now that we have added vertical structure, you can actually have a mean depth, and within that you have equivalent depths Hn. So they are not necessarily the same thing. You have to be careful about that. And the vertical stratification is what makes that difference in terms of H bar and Hn. So relative to the boundary conditions, you set K and H bar, which respond to let's say variability of waves along the ray path, and they have to adjust to keep the intrinsic frequency constant. So the frequencies or eigenfrequencies represent the possible modes of oscillation of the system, which may or may not be excited by some forcing function. So they are normal modes, but doesn't mean they're always excited. The example we saw before, that you have a string on a guitar which is note C, and unless you pluck it, it's not going to be excited. So you need certain matching of the forcing and the normal modes. In a forced system, the frequency omega and the longitudinal scale are given by the characteristics of the forcing function itself. So we'll look at some forcings and how the waves are generated and how they interact with the basic state. Then the equivalent depth is the eigenvalue relative to the particular imposed forcing. So the response of the system is going to determine the equivalent depth, which is obviously going to depend on the background state, the vertical structure, and so on. So let's start by looking for free solutions. This is the vertical structure equation. Looks complicated. I won't say much. We had seen that in 5.33. Here is our forcing function Q dot, which is the diabatic heating term, could be convection in the atmosphere. The other terms are what we already know: beta, omega, k. Epsilon is the gradient of G in the vertical. H is our equivalent depth, and so on. We got the vertical structure function out of it in terms of Zn with these coefficients that we saw before, and the vertical stability function or structure function, so Snz. D squared Zn dz squared plus m squared Zn equals 0 if you set this to 0, as we just did for free waves. And now we add a vertical structure. So we will see two solutions, one where T bar z is constant, so G bar z itself is constant, and epsilon then becomes 0 because this has no gradient in the vertical. In the other case, we look at T changing linearly with height, and then if the gradient reverses sign, as it does in the troposphere to stratosphere, in the stratosphere you have positive gradient with height, and this is G bar, which is BZ plus C. Okay, so that's the scale height. Okay, so once we have that, we can look at the isothermal atmosphere case where we just set Sn equals 0 in this case, and then d squared Zn dz squared plus 1 over G bar squared become multiplied by kg bar over Hn minus 1/4 Zn equal to 0. So this is our vertical harmonic oscillator, and we have G bar RT bar over G, which we already know. There are detailed derivation of boundary conditions. Okay, so this is second order equation, but you have waves propagating up and down, so you end up sometimes needing 4 boundary conditions. In this case, we need a boundary condition at z equal to 0 and a finiteness condition as we go into the upper atmosphere. You cannot have growing solutions, right? That's not physically consistent. So the lower boundary conditions requires that the normally directed velocity at the lower boundary is 0, as I said before. You cannot have flow going into the ocean or land or coming out. We will see that there are details there that will matter later on. So you can set normal vector dot v equal to 0, where n is normal to the surface if you have bottom topography, for example, and generally w equal to dHb dt, which we saw before when we did the Laplace tidal equation into the wave equations. Hb is the height of the bottom surface, so w at z0 as a function of x and y is v dot grad hb xy. This is kind of our relation of the flow over the bottom boundary, which is related to the basic state and the perturbation times dhb dx, which is the variability of the bottom boundary itself, and which can be simplified this way because in a linearized system u bar is much greater than u prime. Okay, if we have a stationary state, then w at z equal to 0 also becomes 0. I won't go into the details, so this is the schematic of it, of the lower boundary. You have a flow here, which is the perturbation velocity written as a function of v0, normal to the bottom boundary, n dot v tilde is 0. This is our mean height z0. Okay, and that's basically what we said here. I won't go into the details of these boundary conditions because there are lots of details there that are better learned with the real physics. Here they are idealized cases, so you can see that if we had our equations from chapter 5 of the dp dz in terms of g rho, so this is our hydrostatic equation with the perturbation. Then we had this relation which combined through elimination of rho bar. Actually these are all caps. The way the book is printed, somehow it translates me into this kind of a moon over p and rho, which is actually rho hat and p hat, perturbation, pressure and density. That's our relation in terms of gamma, where gamma is related to kappa through basically kappa is 1 minus gamma divided by gamma, so it's again ideal gas constants and Cp. That's our G bar again. So that's our wave equation in terms of meridional and zonal perturbation velocities with the meridional pressure gradient. We've eliminated u bar from this to derive our harmonic oscillator, which is this. What are we doing here is essentially adding, typically we have only dealt with the longitudinal waves, and meridional shear or easterly and westerly basic state. Here we are consistently adding the vertical structure, so we are carrying G bar, which comes with gamma and kappa. So now we are writing dV bar dz. Before, for example, when we did the long wave approximation, we had said dV dt equal to 0, and so on and so forth. So there is the relation between kappa, which is R over Cp, and gamma, and that's our relation. Oops, the V0 it went missing here. We wrote that in terms of stream function, so separable into y and z. So what do I want to do with it? Basically, this produces two solutions. One is a sound wave, a wave that propagates vertically. So obviously we are going to deal with vertical boundary conditions and vertical solutions because we are adding the vertical part in this chapter. So in the first solution, you assume that Hn is real and positive. So Hn is greater than 4 kappa G bar. Then the equation 713, which oops, do I want to go this one, the vertical equation, providing exponential solutions of this type. As soon as we say y, because exponential solutions are the so-called external solutions, you see here Zn as a function of z is the a times exponential with z here. Obviously you don't want the solution to grow exponentially with z, so a has to be 0, and this is the negative sign, so this is okay. Out of that we get the scale, the vertical scale, as opposed to the equivalent depth, which is related to the scale height and kappa. Right? That can be written as gamma z0 or gamma RT bar G, where T bar is the vertical temperature gradient, whether it's constant or varying in Z. Okay, so that's our equation, and Gz is proportional to exponential minus 2 minus gamma divided by 2 gamma Z. Since this is minus, we have exponentially decaying solution. So the solution for gammas when Hn is gamma, when Hn is just gamma G bar, then you will get a solution that has equivalent depth of 9,000 meters, 9 kilometer. Whereas if you have Hn that looks this complicated relation, then you end up with a oscillatory solution with H varying with vertical wave number. Okay, so as we did before, we found Rossby waves, inertial gravity waves, Kelvin wave, mixed Rossby gravity waves, and so on. In the vertical, we are finding oscillatory solutions and this solution that is where the equivalent depth is very large, and it is not allowed in numerical solutions because it moves so fast that if you know numerical methods for the resolution in space and time, it creates numerical instabilities. So typically that wave called the Lamb wave, which moves at the speed of sound, is filtered out. Okay, in the second solution, Hn is real and positive, but it is less than 4 kappa G bar. So then kappa G bar or Hn is less than 1/4. So the solutions of the vertical structure then become oscillatory. Okay, so m in this case is the vertical wave number given by this, which is positive. So it's a downward propagating wave. So we can combine the wave equation with the boundary condition at z equals 0 and write the solution for the waveform in terms of these coefficients E and F, and cosine and sine functions with vertical wave numbers. So in this case, m times e is given by this. So the relation between these coefficients is this. Then these equations give you wave number and the vertical scale of the solution. Okay, so hm is a function of for a given wave number, the equivalent depth is a function of this length scale, height scale, multiplied by this function of vertical wave number. I mean, just get to the physics. This is all complicated. Various assumptions go into this. So equation 7.22 remains positive and the solutions are oscillatory for Hn less than 9,000 meters, which is the first solution we have. After which the mode is so deep, the atmosphere is essentially equivalent barotropic. Remember we had barotropic before, where grad rho and grad p are parallel to each other, so grad rho cross grad p becomes 0. Sorry, that's barotropic. In this case, equivalent barotropic means you're allowing for temperature gradients, but constant temperature lines are parallel to height gradients on a constant pressure surface. Basically, it means there are no vertical shears like thermal winds in this case. Okay, so you allow for gradient, but you make for special cases. So let's make it more specific in the next podcast. This got a little bit long, and it's a bit boring for me to record it as well, because there's a lot of equations, and we are going to make it more specific as we go forward.